All right, guys, let's start with differential estimate of change. Let's start with the definition, okay? Let f of x be differentiable, at x equals to a. Give me some space here to draw a picture of this, so don't write all there. The approximate change in the value of f, which is y, okay, when x changes from a to a plus dx is d of f equals to f prime of a times dx. So I'm going to give you two pictures. The first one, it's a difficult picture with all of the formal lettering and verbiage. And the second one, like a straight up simple example, okay? So this is the first one. Like I said, the first one's kind of difficult to understand, but that's okay. I'll give you another one soon. So let's pick A right here. Then I want to pick the change in A, so let's pick this spot. So A plus that dx. So you have two x locations. One is A, and then one is A plus dx. So if I pick A, then this value right here, well, let's label this. This is the x coordinate, and this is the y coordinate, which is also f of x, okay? So if I pick A, would you agree this blue distance that I just got done doing is the y value of A? So in theory, it's f of A, okay? So that's a y value. If I pick A plus dx, that space to the right, then this right here is the change in x, which is called dx, okay? Again, dx is the change in x. We also use linearization to approximate using line to approximate the value at A. So let's draw this really quickly. And this is a sketch, so don't hold me to my line. So this is my line, L, which is linear, oops, can't spell linear, linearization at A. Well, if you look at this, okay, so this is what it's saying. So we know dx is the change in x, okay? We picked A plus dx, which is this dot right here, is the, okay, it's all the way over here. Would you agree this is f of A plus dx? Okay, well, then what does that mean? That means this space right here, which is, by the way, the same as this space right here, okay, is the change in y, right? Which means the change in y, which means change in y, which is the same thing as saying the change in f, since it's f of x, okay, the change in f of x. Well, the change in y is y2 minus y1. Well, y2 is f of A plus dx minus f of A. This right here is the actual change of y, okay? Well, what is the approximation then? That's what it's really, this whole definition is about. Well, then what is really the approximate change value of y? Well, then it's really this piece right here, which I'm going to use red, okay? This piece, from here to here, okay? That right there is the approximation, it's a change, okay? And, well, that's the difference in linearization. Well, by definition, it's f prime of A times dx, which is a change in x, which, as you know, that is the approximation change in y, okay, from A to A plus dx. So this is what they're really saying. That right there is what they're saying. Now I'm going to draw another picture which is a little bit simpler so we can get a better understanding, like a line. Okay? I'm going to give you an equation of a line. Super easy. I'm going to make some tick marks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And let's start with, let's just give us y equals 2x. This is a made-up line. Okay? No big deal. Start at 0, go up 2 over 1, up 2 over 1. Here's our made-up line. And again, this is completely made up, so we have a better understanding of this. Then let's go and pick a right here. This is a. And our next tick mark is a plus dx. Would you agree? Okay, a plus dx, because I picked a is 1, a plus dx is right here. So this is the change in dx. So dx right now, dx is 1 unit. Well, I can't have s. 1 unit. So what is the approximation for the change in y? Well, based on the formula, the approximation for change in y, which is this formula they gave us, is the first derivative of at a. So if I gave you y equals 2x, y prime is 2, times the change in dx, the change in x, which is dx, which is 1. So the approximation of the change in y, if I were to go from a to a plus dx, is 2 units. Should be 2 units, okay? Well, is that true? Is this 2 units? Sure it is. So that's what it's really saying. If it's a curvature, we are using derivative to approximate. So it's not always the actual. It's not always the exact. But it's good enough for us because it's easier to approximate, okay? So that's what this theorem is really saying. Well, let's use it right away to apply to example 6. For each of the following, the function f changes value when x changes from a to a plus bx. I believe that's really needed to be fixed to dx. Find, part A, the absolute change, okay, which is the actual change. Then B, estimate the change. What this question is really doing is, do you see much difference? Okay, is it that much of a difference? That's what it's saying. And C, approximate the area. That means you need to subtract the actual and the approximation. So part A, we want to find the actual change, the absolute change. So actual change is the y2 minus y1. Okay, in this case, it's f of a plus dx minus f of a. And they gave you a is 1, dx is 0.1 minus f of 1. So this is really f of 1.1 minus f of 1. And then we just have to plug it in. So first bracket, ready. 1.1 to the third minus 1.1. Close that up, take away 1 to the third minus 1. This is going to give me 1.3, oops, that doesn't look like anything. This is going to give me equals 1.331, take away 1.1, box that up, minus 0. So that's going to give me 0.231. So that is my actual change. Then B, use our approximated change formula, which is the change in y. It's the first derivative at a times the change in x. Well, let's do first derivative then. The first derivative is going to be 3 y prime is equals to 3x squared minus 1. Then your x is evaluated at 1. So this is going to come out to be 3 times 1 minus 1, which is going to be 2. So df is 2 times 0.1, which is dx. Remember, dx is given to you right here. So that will give me a 0.2. So the approximated formula is 0.2, and the actual change is really 0.231. As you can see, it's a small gap. Okay, so that's what part C is asking. Find the error, which is an absolute value. So you're going to take 0.231 minus 0.2. This will give you a change of 0.31. That's not that big of a difference in terms of the actual and the approximation. Okay, let's try this one. Is this one going to give us a bigger error or smaller error? So again, same thing. We want to find the actual change first, which is y of 2 minus y of 1, or y of x2 minus y of x1. Okay, for this one, f of a is 1 plus 0.01 minus f of 1. Let's plug it in. Well, let's simplify that. F of 1.01 minus f of 1. So here we go. 01 to the fourth minus 1 to the fourth. This is going to give me 0.0406. Even though I didn't tell you how to round, it's such a small number. When it's a small number, you want to carry it out enough so we can understand the difference. Then B, it's the approximate change, which the formula says f of x is the first derivative at a times the change in x. So let's do the first derivative. F prime of x is 4x to the third. I need to evaluate it when a is at 1, so this is going to be 4. So d of f equals 4 times the change in x, which is 0.01. This is going to give me the answer of 0.04. Okay, so an error analysis tells me that absolute value of 0.0406, take away 0.04, this is going to give me a change, a very small difference between an actual y change from a to a plus dx to the approximation. Okay, so it's a very, very small change, which is good. The smaller the error, then the better it is for the approximated formula. Okay, and I suppose this is, well, let me give you a joke before I call it an egg roll. Well, how do you make a goldfish old? How do you make a goldfish old? Take away the G. Yeah, G. This is an egg roll.